Good evening, all. And I take just 1 minute to introduce this group. Science People is a small group with which we wanted to kind of propagate science in a kind of normal man's language. And we have been conducting this kind of lectures for the last 2 years. I mean, this is the 55th lecture come demonstration kind of thing. The basic idea of this group is to take science to all those who are interested in science. I mean, basically to connect the lab to the common man. I mean, science should not be confined to the labs, so it should reach the people, and that is the idea. So today we have a lecture on how to take photography, especially the celestial photography. So to introduce the subject and to the speaker, I would like to introduce TNN, my friend. Please take over. Thank you so much.
Thank you. Good evening, all. It's my pleasure to introduce, with privilege, let me say, my own student, Rajan Jain. And Rajan is currently is a junior research fellow in my laboratory at TIFR Hyderabad. And where he is working towards the development of some composites based protective equipments. I mean, in simple words, helmets. That's a different topic, not today's topic of discussion. But Rajan has a variety of interest and has a very interesting training background. Prior to joining TIFR, he completed his BTech in mechanical engineering from VIT, and then MS in aeronautics from Purdue University, USA. And now he's, as I told you, from last 1 year, he's working in my laboratory. But after then, in August, he's going to join for his PhD program at one of the prestigious universities in USA, University of Colorado Boulder, in mechanical engineering. Very recently only I came to know about his passion on astrophotography. Not just passion, he's kind of trained on that, and he could also able to teach us very nice aspects of astrophotography and how to get good images. In few of his lectures happen in TIFR very recently. I was highly impressed, and the kind of feedback we received from his talk and then the workshop. I hope you will also enjoy his talk. So let me invite Rajan for his talk on a glimpse into astrophotography. Rajan, please.
Thank you so much, sir, for the introduction. Am I visible and audible?
Yes, very much.
All right. So thank you so much for introducing me. And it's actually my honor to just share my hobby with you all so that I can give you a glimpse into what astrophotography is. So starting with this, I'd like to share my screen with you. And I hope you are able to see my screen.
Yes.
Yes?
Yes.
It's getting shared, yes.
All right. So today I'm just going to talk about what astrophotography is, and I will try my best to get you interested into this little hobby of mine, which you can probably pursue or just do something for fun. So as TNN already introduced me, I have an engineering background in mechanical engineering and aerospace engineering from VIT Vellore and Purdue University, respectively. So I was a member of SEDS, which is a club called Students for Exploration and Development of Space. And it's an international student-led organization which promotes the awareness about space. So this is where I actually began my journey into this field. And ever since then, it has been 6 years ever since I delved into this. And currently I'm working as a GRF. So moving on to the main subject of this presentation, you might ask yourself, what is astrophotography? Well, it's really simple. The photography of any astronomical or astrophysical object. And usually you might think that, okay, astronomy, that means you need to do this in the night. But not necessarily. You can click a picture of the sun. I mean, that's how the first astrophotograph was actually clicked. So moving on to the history of astrophotography, the first astrophotograph that was clicked was sometime in 1851, and it was a total solar eclipse that you can see. Let me just use the laser pointer. So the picture that you see is a picture of the sun, which is occluded by the moon. And the bright ring around the moon that you see is nothing but the annular disk of the sun. And on the bottom left, you can see a picture of the Orion Nebula that was clicked in 1880. This is the first documented photograph of the Orion Nebula. And 3 years later, after some improvements in techniques, people were able to click a more detailed picture of the Orion Nebula. And this is a nebula that is very well and easily visible to our naked eyes. So if you look up in the sky during the winter time, you can possibly try to spot this nebula, and it's within the Orion constellation. Now, talking about the solar photography. Now, this is a picture of the sun that was clicked through a telescope with a solar filter attached in front of it. It should be noted that there should be no way that you look at the sun without using specialized optics, because the intense light from the sun, which when focused through the optics, can actually burn through your eyes. So, and if not your eyes, it can set fire to nearby articles, like easily flammable articles like wooden clothes. So you need to be extremely careful when you're looking at the sun. Now, on a lighter note, you can look at the sun through a telescope twice. Once with your right eye, and once it's burned out, you have your left eye to look at it. So you can look at the sun twice. Anyway, so the moon is another yet frequently photographed object. The picture on the left shows a partially lit moon, whereas the picture on the right shows the moon where it is illuminated by earthshine. Now, earthshine is basically the light from Earth that is reflected off of it, and which hits the moon and illuminates it, but not as much as the moon gets illuminated by the sun. So you see a very faint shadow, which is clearly the shape of the unlit part of the moon, and that is the earthshine. And the picture and the dot on the top is actually Jupiter. Next, this is a picture of the sun during a sunset, and you can see there are some active sunspots visible in the center left area. And this was a safe time to click the picture because there was a lot of clouds that were occluding the sun, although you do not see the clouds in this picture because the focus is on the sun and not the clouds themselves. And during sunset, the intensity of the light is very less. And the reddish tinge that you see here is caused by a scattering at the horizon, scattering of light. Next, here is a wide field view of the winter Milky Way, which shows plenty of stars in our galactic neighborhood. It might astound you, but there are about 67,000 stars in this photograph. While they may not be clearly visible, I used image processing software to find out the exact number of stars, and it was well above 67,000. Here is a picture of a planet. Now this is Jupiter, although you do not see the Jupiter that you're acquainted with, one with the banding structure and the great red spot, but this was clicked through a very amateur camera, and this was during just about the start of my hobby, so this is not a very good picture, but here you can see Jupiter with its 4 major satellites, which are Ganymede, Io, Europa, and Callisto. Now, it's a fun fact that Ganymede is the largest satellite in the solar system. And Io is a satellite of Jupiter, which is completely covered by volcanoes. And Europa is an icy satellite. So Jupiter has a wide variety of satellites, which have all sorts of climates on them. Now here on the left, the photograph on the left shows the Pleiades star cluster. Now this is an open cluster which is easily visible to the naked eye. And along with this, you can actually even see two tiny meteors, which were going about just when I clicked the photograph. And this was clicked in December. It's a winter star cluster, which you're able to see. And I clicked this from Mahabaleshwar, which is a hill station in Maharashtra. On the same night, I also was able to click the Orion Nebula, although you may notice that this is not as zoomed in and visible as the previous astrophotographs I showed you, the one clicked in 1883. But this is a wide field picture of the same nebula, which was clicked during the same winter. It can be noted that with your naked eyes, you can easily see the nebulosity or the cloudiness in this object. And you can, if you have a small pair of binoculars or a small telescope, you should be able to see the structure of it very clearly as well. Now here is a photograph of the comet Neowise, which approached very close to Earth during July last year. And the comet and the tail are very easily visible to the naked eyes for about 2 weeks. Now you may see that the color of this comet is green, and this green color actually comes from the ionization of diatomic carbon, which is C2. Now the nebulae are yet another important type of targets for astrophotographers, particularly for their beautiful colors and intricate and intriguing structures. By nature, these are humongous clouds of interstellar gas where stars form. And depending on the types, they can be classified into various types of nebulae. So the first one is like a reflection nebula, that the one that you see on your left, right here. And the example that I've shown here is a portion of the M20, which is a Messier object. And this is the Trifid Nebula. Now, these are nebulae which reflect the light from nearby stars. All right, so it's just a cloud of gas which is reflecting the light of a neighboring star or a group of stars. Next come the Emission Nebulae, or also supernova remnants. And these are like this portion that you see right here is a portion of the Whale Nebula. And these are clouds of hot gas which emit light of their own. Now, this light may not exactly be in the visible range of wavelength, okay? Like the visible light that you see, which is starting from blue to red, is actually a very small part of the electromagnetic spectrum. And most of these nebulae do not actually emit light in that region. They can emit light in the infrared region, which is invisible to us, the UV light, which is again invisible, X-rays, or even gamma rays, which are again not visible to the human eye. But there are specialized cameras that can pick up light from these objects, and we can try to translate them into visible wavelength by just assigning a few colors. Next come the dark nebulae. And the one that you see here is a very well-known and a very common dark nebula that people used to describe these type of nebulae, and this is called the Horsehead Nebula. Now, if you have a very powerful set of binoculars, you might be able to very faintly see this object near the Orion's belt. But these are basically just clouds of gases so thick that they do not allow light to pass through them. Thereby, they look like shadows in the colorful background. All right. And the fourth type of nebula is a planetary nebula. Although this name is misleading because planetary nebulae have nothing to do with planets. Now, these were named as planetary nebulae because when old astronomers, astronomers in the olden times looked at them, they looked like small circular disks, and disks often referred to as planets when it comes to astronomy. When you look at any planet through a telescope, say maybe Jupiter or Saturn, you'll see a disk instead of a pinpoint. And these nebulae, which people did not really know about in the olden times, they look like small disks. And that's why people thought, okay, these might be planets, but it's not a planet. It looks like a cloud of gas. So let me just call it a planetary nebula. So that's how the name was termed. So way these are formed is basically when a star comes towards its end of life, the radiation pressure exerted by the star cannot withstand the immense force of gravity. Therefore, the star collapses upon itself. And when it does so, the star, if it is about 10 times as massive as the sun, it collapses into a white dwarf, which is a very compact star. Okay. And then it expels its outer layers in the form of this planetary nebula. Now, the one that you see here, it has a distinct S-shaped like cloud of gas, which is escaping the white dwarf, which is at the center of this figure. Although you cannot see the white dwarf because it's very tiny as compared to the spread of this nebula. Finally, if you have if the mass of your star is more than 10 times the mass of sun, you will end up with something called a supernova. And a supernova is basically the same as the nova, except it's extremely more massive and powerful than that. So in this case, the star explodes in the form of a supernova, and the core either collapses into a super dense neutron star or a black hole. So which leaves behind a supernova remnant. Now, M1, which is a Crab nebula, it is not very easily visible to the naked eye, but if you have a powerful telescope or a mid-power telescope, you should be able to see this as well. But here's something about the last couple of slides. To observe nebulae, you need to be in a very clear and dark environment. And the bottle scale was developed in 2001 by a scientist called John Bottle. It's a scale which tells us how clear the sky is. Now this scale ranges from 1 to 9, with 9 being the inner city sky where you don't really see any celestial object, and 1 being an excellent dark site where you see almost everything that the universe has to offer. Now, like modern cities, like if you live in a modern city or even a large town, you may have your Amazon and Swiggy deliver 24/7, right? Now that's a big thing. People like their deliveries on time. But what you're missing out on is when you go into a larger human civilization, like when your settlement size is very big, you have lots of buildings and lots of malls, you have roads, and all of them have one common thing: light, artificial light. So the artificial light blocks out all the natural light that you see here, and it gives us something very similar to this in the night sky. So where I'm currently right now, Hyderabad, I fall under the bottle sky zone class 6. Okay, so even on the best day, I might be able to see something like this. However, if I go to a more remote place, all right, like I go on the outskirts of Hyderabad, or maybe some like a village which is nearby, I'll probably see something like this. All right, so now these are two websites, lightpollutionmap.info and darksitefinder.com. These actually show you the current, like they take your location and they tell you what kind of sky you're living in. And they also show you a map around your location so that you can find a dark site near you in case you ever want to pursue astrophotography. So that's where I am. So there are a few stargazing sites in India. While these places may be remote, the list of the places in the left column offer the best stargazing sites within the country, and they have a bottle sky rating of 1 to 2. Let me remind you, 1 to 2 basically means this. Here you can easily see the Milky Way with your naked eyes, and what you consider as light pollution, like for example, you're trying to look at the sky and you see a street light in front of you. That light will actually block out a lot of the stars because your eyes get accustomed to the brighter light and you don't see the fainter objects. Now, the same thing applies in the bottle scale 1 and 2 class skies, where the moon, which is a celestial object, it's a natural source. We did not put any artificial lights on it, but the moon becomes like a nuisance, because the light from the moon becomes so bright that fainter objects that are visible in the night sky become invisible due to that. Therefore, astronomers usually prefer moonless nights or new moon nights in order to observe dark skies. So Pangong Lake, Ladakh, Indian Astronomical Observatory, Ladakh, Nubra Valley, and Leh Ladakh, Spiti Valley, Himachal Pradesh, Run of Kutch, Gujarat. These are one of the best stargazing spots that you can ever go to, ever find in India. And the list on the right basically just shows you like a few other good places that are in and around Andhra Pradesh, for example. So when it comes to bottle skies of 4 or above, you have the moon, Venus, and Jupiter that you totally can see, and you want to see them because they are the only celestial objects that you can find. So the three other main the three main settings that you need to know about if you're doing astrophotography are aperture, shutter speed, and ISO. Now, aperture basically means relates to your opening of the lens. It is the part of your lens which allows the light to come in, and a wider aperture relates to a more opening in your lens, which allows more light to fall on the sensor in a per unit amount of time. If you have a wide sensor, like a wide aperture, that means more light is allowed into the sensor. That means you get a brighter image. And if you have a narrower aperture, only a small amount of light hits the sensor per unit time. Therefore, when you're doing astrophotography, it is very important to have a wide aperture because that allows you to capture more light in less time. That leads to the nomenclature called a fast lens. So when you talk about photography, you talk about the speed about the lens. And the speed of the lens is fast when it has a wide aperture. All right. Now, these apertures are usually denoted as fractions, and they're related as f upon a number. All right. So say f by 2 is a wide aperture, and f by 22, which is a small aperture. All right. Because 1 upon 2 is 0.5 and 1 upon 22 is less than 0.05, right? So this leads to more light collection at f by 2 and less light collection at f by 22. The next setting is called the shutter speed, and it basically is the amount of time the sensor is exposed to light. When you talk about shutter speed, it is usually denoted in seconds. And if you're clicking a photograph, you might see that you'll see a fraction at the end of your photograph, which is say maybe 1 upon 100 or 1 upon 160. Now, these are nothing but the duration of time that the sensor of your camera was exposed to light. All right. So for example, if your photograph has a shutter speed of 1 by 200 seconds, that means your shutter opened and closed in a matter of 0.005 seconds, and it captured the light coming into the sensor in that interval of time. When you're doing astrophotography, because these objects are very faint and far away, you need to have a longer shutter speed. Okay, now I'm talking about 1 second, 2 seconds, 3 seconds, and so on. But when it comes to imaging galaxies, these shutter speeds need to be very, very high. Now, by very high, I mean you need about 8 hours of light data. 8 hours is basically 8 into 60, which is 480, and into 60 number of seconds. Now, it's not really possible and practical to have a single shot which is maybe 8 hours long, because the Earth does not stay still. The Earth is rotating about its axis, and in doing so, the sky keeps moving. It appears to move because when you see the moon at say maybe 10 o'clock in the night, it is at a certain point in the sky. You maybe look at it after 1 hour, its place in the sky has changed. Now, why does that happen? Now, that happens because of the rotation of Earth. All right. So when the Earth rotates, it appears to us as if the sky around us is rotating or moving about. But we don't see the sky moving up. We don't see the Earth rotating because we are on Earth, and that is our non-inertial frame of reference. All right. So 8 hours of light data is not really practical and applicable because you might start your photography at, say, 2 a.m. in the night, but by the time it's 8 hours, it will already be 10 a.m. and everything will be bright. So your photograph will be spoiled. So in order to make sure you don't fall into such problems, you have something called a star tracker. Now, star tracker is a device that rotates about the Earth's axis at the same speed as Earth is rotating. Now, this rotation basically keeps your entire object into view, because if you're looking at the moon and the moon is tracking across the sky, all right, if you'll just keep your camera straight and let the moon go, you'll see the moon move as a streak. But to capture all the details of the moon, you need to move along with the moon. Now, when you're doing that, you want to point your camera at the moon when it does so. And in doing so, you can capture this data on multiple days. For example, I go on Saturday and Sunday. Saturday night, I click 4 hours. Sunday night, I click 4 hours. Now, adding that up will give me my 8 hours of light data, and I did not even have to stay out for 8 hours on a single night. All right. And the third setting that we talk about is ISO. Now, ISO is a sensitivity of your sensor. Okay. And it has different values ranging from 100 going up to all the way to 12,500 on my camera, but it can go to a higher values on your camera. Okay. Now, this number is basically a standard. And ISO basically means the sensitivity, as I just mentioned. And a higher ISO setting on your camera basically means that you're inputting more current into your sensor. When you're putting in more current to your sensor, you are able to capture even the fainter part of the photograph that you don't see. Okay, but the goal of this, the goal of astrophotography is to make sure that you have the perfect ratio of the perfect balance between shutter speed, aperture, and ISO. Right.
Rajan, your laptop is ready now?
Yes, I'm just checking.
Hmm.
So the goal of astrophotography, as I mentioned, is to have a perfect balance between these elements. Okay. Now, the next section that I was going to talk about was going to include some photographs. I'm just trying to get them up as we speak. And I was going to talk about lunar photography. So when lunar photography is concerned, your subject is the moon, and the moon is a very bright object in the night sky as compared to maybe the stars or nebulae. All right, the moon is very visible to the naked eyes, and it can be seen easily. Now, when it comes to astrophotography of the moon, you need to know that if you have a shutter speed, you need something fast. Okay, and by fast I mean you need to be a fraction of a second and not a full second. And the reason behind this is because the moon is so bright that if you let your sensor of your camera open for too long, your photo will become overexposed. You will just see a white circle without any details on the moon. But if you slow down, if you speed up your shutter speed to say maybe 1/500 seconds, okay, that gives your camera 0.002 seconds to click the picture, thereby allowing it to capture all the details on the moon. And the aperture in this case should be something upon f/8, because you want to capture the moon with all its depth of field. You do not want to have only a certain part of the moon in focus. You want the entire moon to be in focus. And when you're clicking the picture of the moon, you want the picture to be as less grainy as possible. and the grains are usually introduced into the photograph by a high ISO. So when you have a low ISO, say maybe a setting of ISO 100, which is usually the minimum, you will get a photograph which is very good in the terms of graininess. You will not have any grains, and with shutter speeds of 1/500 seconds and a f-stop of f/8, the aperture of f/8, you will have a very good clear picture of the moon, right? I think my slide is just loaded. Let me just try to pull this up. TNN sir, is it possible for me to share the slides with you so that you can share them?
Yeah, please do that. Please do
Yes,
that.
sir. Sir, I've shared it with you.
Okay, I got it. Can you
So
see?
if you could, yes, sir. So can you go to slide number 17?
Yeah. Rajan.
Okay. Yes, I can see your slide now. Okay, so you're able to see the screen, everyone?
Yeah. Yes.
Okay. So this is what I wanted to talk about. So you have the three different main functions, which is aperture, shutter speed, and ISO, which you need to control in order to click a good astrophotograph. So can you move to the next slide? So aperture, again, is the opening of the lens. And when it comes to the opening of the lens, you include more light in the lens. Okay, so the picture on the far left that you see with the girl's face and flowers in the background is the one clicked with the f/1.4, f by 1.4. Now this is allows for more light. Okay, and when you have uh, f number which is small or a wide aperture, you just have the subject in focus. The background automatically becomes blurred out because you have a shallow depth of focus. And as you move to f/22, as you see on the rightmost picture, you take in, although your picture is sharp, your subject as well as the background are in focus. Okay, so when you do astrophotography, it's good to have a number which is say f/1.4 or f/2 so that you allow more light in the photograph. Okay, so can you go to the next slide? I was going to perform a live example, but it would not be possible today because of like some hardware problem with my laptop, but I will talk about shutter speed now. Now, when you want a blurred motion, say maybe you're taking a picture of a fountain or maybe trying to take star trails, you want a slow shutter speed. And the shutter speed is again the amount of time that your sensor is exposed to light. And when you want a crisp picture, a picture of each and every particle in that photograph in your field of view as it is without it trailing, you want a fast shutter speed, say 1/2000 seconds, or it can even be 1/4000 seconds. Now, when you're doing astrophotography, if you want to click picture of a planet or a star, okay, you want to use the frozen motion. Okay, you want to use a fast shutter speed so that you don't blur any details on that picture. But if you're doing a wide field astrophotography where you want to click star trails, you use a blurred motion. So next slide, please. After this. And ISO, as I was explaining, relates to the amount of current that is passing through your sensor. If you want a clean image with very less grains, you go for a lower number of ISO. And if you're in a low lighting setting, and for example, when you click on a low light option in your camera or on even zoom, what it exactly does is it passes more current through the circuit and it allows your sensor to be more sensitive to light. Okay, so it picks up light even from very dim areas, but in doing so, your image becomes a little grainy. So next slide. So what you need for a clear dark sky to do astrophotography is you need a clear dark sky with preferably low winds and humidity. And you're talking about low winds and humidity because this can lead to aberrations in your photographs. And if you don't have any problems spending some money, you can invest in binoculars and buying a telescope. But if you're doing very basic astrophotography, just a camera, tripod, and laptop is required for you to do so. So next slide. So what are you looking at? So for example, you just go in the night sky and you look up at the sky. You don't know what star is, what dot in the night sky is what star, right? So in order to help you out, Stellarium is an app which can help you find the location of any given object in the night sky. And this is a free open source planetarium based software, which you can download on any device. And all you have to do is enter the date, time, and location, and it will calibrate everything on its own. And you can locate any object in the night sky, including SpaceX, Starlink satellites. It's very cool. So next slide. So before you begin astrophotography, there are 6 main rules. So the first one is you have to be on manual mode so that you're able to control your aperture, shutter speed, and ISO all together. You don't want to autofocus because the way autofocus works is that the light from the image is actually calibrating the sensor, the distance sensor on your camera, and it tries to find the best focus. But when you do astrophotography, everything is pitch black. The moon and the stars are not very reliable and sturdy sources of light, and therefore it leads to poor autofocus. So you can just turn your autofocus off to give you the best focus. And you must click raw images because raw images contain the maximum amount of data. And using that, you can obtain very clear photographs and bring out the maximum detail in each photograph. The next slide. Next is dark adaptation. Dark adaptation is basically you moving from a bright environment to a dark environment. And it takes about 25 minutes for the human eye to adapt to a dark environment. And in order to clearly see the dark objects and the distant objects, you must allow your eyes to adapt to the dark very perfectly. And white light is a total no. You cannot use a flashlight or any like your mobile screen or your laptop screen because it interferes with your dark adaptation, and you would have to undergo another 25 minutes of wait time in order to adapt your eyes to the dark. However, if you want to use red light, like a red colored torch or a white torch which is covered with red paper, you can do so and it will not interfere with your dark adaptation. So next photograph. So here is a picture of the moon, and I'm going to talk about lunar photography. Next slide. So as I mentioned before, you would have the 3 settings, which is shutter speed, aperture, and ISO to play with. And when you're taking a picture of the moon, you want to keep it between 1/800 to 1/40 seconds. Now, this is my personal experience, and it may totally differ from person to person depending on the kind of environment they have in the night sky. So I'm keeping a very fast shutter speed in order to keep my image sharp, yet allow enough light to enter the camera to capture all the details. And the aperture, I keep between f/4 or a lesser amount, which is f/5 or f/6, to allow for more light in the image while keeping the image sharp. I do not go for f1.8 or f/2 in this case because I do not want a lot of light because all my details will get just washed out. And the third setting is ISO. And I keep it between 100 to 800 to allow for a good balance between shutter speed and aperture. But again, a higher ISO means more grains, and I want to reduce that as much as possible. So I keep it to a low number. So my ISO is usually ranging between 100 to 800 and not 1600 or 3200. Next slide. So this is the raw picture of the moon as you see on the left. Now this picture is something you would see straight out of the camera. And if you process it, in a image processing software, you would see something as the picture on the right. Now, in the picture on the right basically has adjustments made to its exposure, brightness, contrast, whites, and blacks. Next slide. An interesting fact to know that out of the Apollo program, there are 6 landing sites on the moon, which are visible to the human eye when you look at the moon. I mean, you cannot see the landing site itself, but they're right there in front of you. And it's very nice to know that you can actually see how far the human space exploration has gone. And these 6 sites on the moon are just a basic example of that. Next slide. So supermoon, like many of you must have heard the term supermoon. Now, what exactly is the supermoon? It's basically the moon during its perigee, which is perigee is nothing but the closest point to Earth in orbit. Okay, the average distance of Earth to moon is 384,000 kilometers, but during a supermoon, the distance between moon and Earth goes down to less than 360,000 kilometers. And this allows the moon, because of this closeness and distance, the moon appears about 15% larger than usual. That's why it's called the supermoon. So next slide. Now this is a screenshot from the software called Stellarium that I mentioned earlier. And here you can see that the moon is right visible right there. And you also have the different constellations around it. And this picture is from early June when the supermoon occurred. And the moon was right at the cusp of the Sagittarius constellation. So next slide. And Sagittarius is a famous constellation because the Milky Way is the Milky Way's core passes right through Sagittarius, and the moon was very visible through that. So next slide. Now, why, although the Milky Way passed behind the moon and the sky was clear, but you would not be able to see the Milky Way, right? Now, why is this happening? Now think of this as, so the previous slide, please. Right. So why does this happen? It happens because when you move, for example, you go to a theater, okay? And as soon as you enter the theater hall, it's very dark inside. But while you were entering the theater, it was very bright outside, right? So when you have a bright object in front of a fainter object, the fainter object just gets washed out because your eyes are accustomed to the brightness, and everything that is in the faintness just does not appear. Okay, that's why you cannot see the Milky Way when you have the full moon or any other bright source of light in your surroundings. So next slide. So the next type of photography is the wide field astrophotography. And the picture that you see right here is a picture of a star trail. And this was clicked in Mahabaleshwar during my visit in winter of 2016. Next slide. So the effect of focal length is something that I'd like to talk about. And this will actually just show you what I exactly mean by rotation of the Earth. So this is a real-time video, okay? I'm not speeding it up, but all you can see is the part of the moon that you see in the video is slowly moving down. I am not moving the camera, and the camera is very still on a tripod, but the reason the moon appears to be setting is because of Earth's rotation, okay? So the higher the focal length, the faster your object will move out of the field of view. There you can see that the moon is already setting, and this set in about 30 seconds. The next slide. So when you're talking about star trails, you want the stars to move out of the field of view because you want to capture the path that the star will travel through when the Earth is rotating, right? So in order to capture star trails, you want to use a slow shutter speed. So I use something between 4 seconds to 150 seconds. It can even be longer than that if you wish, but I found that these settings usually work pretty good. And to capture, there is a small mathematical formula that you can use to determine how long your shutter speed needs to be, like the minimum amount of shutter speed. So it is 500 divided by 1.6 into your focal length. Okay. So if, for example, if I'm using a 200 focal length, so my stars will start trailing if I use the shutter speed of 500 divided by 320, which is less than about 1.67. So if I use anything above 1.67 seconds, my stars will not be dots. They will start to look like elongated lines. My aperture again needs to be about 4.5 or lesser to allow for better depth of focus so that I don't focus on just one part. And ISO, I want to keep it on a lower end so that I allow for lesser noise and optimal lighting. And finally, I stack all these images in a software called StarStax, which is again a free software to use. So the star trail that you just saw before actually was a collection of around 40 photographs that were clicked during an interval of 1 hour and 10 minutes. And the first picture that you see, the picture on the left, is basically the picture at the time t equal to 0. And this is when I used a 30-second exposure. Now I was shooting this with a 10 millimeter lens. So my star trail period was basically 500 divided by 160. Okay. Now that is about 3 point something seconds, right? If I'm not wrong. And sorry, 30 point something seconds. So I used an exposure time of 30 and I started to click this photograph, but I realized that that star trail wasn't enough for me. So I decided to go for a higher amount of shutter speed, which I went up to 130 seconds. And at 130 seconds in the picture on the right, you can see that the stars don't appear as dots anymore. They appear like small elongated smudges. Okay, next picture. So this is the motion of the stars over 1 hour and 8 minutes. And this is the final image that you get when you stack all those images. So when you use a slow shutter speed, which is basically a big number of shutter speed, you end up with something looking like this. Next slide. And this is a small video of the motion of the stars as they appear to move. So can you replay it? So here you can see that the stars appear to move in the upward direction, and each individual frame of that photograph of this video was stacked to achieve the photograph in the previous one. So I was going to start like a visual activity by doing something called light painting, where you basically do the same settings as star trails, but you apply that to a civic environment. Okay, so can you go to the next slide? Now what you see in front of you is not really any computer graphic. Now it's just a picture of it's a telescope through which my camera was attached, and this orange line that you see, the orange design that you see, is nothing but my finger in front of my camera flash, and I'm just moving my hand about in front of the camera. And the way I actually click this picture is using the settings that I will show in the next page. So can you go to the next slide? So I use a shutter speed of between 10 to 20 seconds to capture the trail of light that I want to draw. Okay. And then I use the aperture of less than f/4 to allow for optimal depth of focus. And because it's already very dark using these settings, I go for an aperture of an ISO of about 400 to 1000 to capture all the light in the background and the subject easily. Okay, so this is something that I encourage you to try. You can do this even with your mobile cameras if you have the Pro mode, or just download something for like a Pro camera on your phone and you can try this out. So this was my session for today, and the next part of this session was actually a part how to process this image. Okay, but I would not talk about this right now because this is a whole another section and it requires people to have their own laptops and images that I would provide to them. So this is how I'd like to end my presentation for today. If anyone has any questions, I request them to just ask me, or you can send them to TNN via chat.